Hello everyone, this is Dr. Zach again with AP Calculus. So for today's lesson, we are going to use an initial value in order to determine a particular solution. So when we have a general solution, we have plus C left in our problem. But if we find a particular solution, we're going to be able to figure out that C value. Afterwards, we're going to solve some position, velocity, and acceleration problems. Let's get started. For your lesson preview, you were given a differential equation and asked to find the original function y. So hopefully by the end of class, if you weren't able to do so already, you came up with y equals x to the third plus x plus 2. And for question B, things got a little bit more intense. Y equals x plus cosecant x. Don't forget that would be a positive cosecant x plus 12 minus 2 root 3 minus pi, all divided by 3. Now, if you weren't able to figure those out, that is why we will discuss examples 1 and 2. So, for example 1, you were given your equation, and you might want to rewrite it so that dy equals your function with a dx. And once it's written so that you separated your variables, y is on one side, x is on the other, then you're able to integrate both sides of this equation. Y equals, and after you have integrated, you come up with 3x cubed minus your 2x squared plus 5x plus your c. Now remember, when you have the plus c, this is when you have a general solution. That means your c value can take on any number, 0, 1, 7, whatever you feel like. But you were told very specifically that y at -1 equals 0, or that x equals -1 when your y value is equal to 0. In which case we can substitute. 0 equals 3 times -1 to the third minus 2 times -1 squared plus 5 times -1. Next we're going to solve for c, and you come up with 10 is equal to your c value. So if 10 is equal to c, you can find your particular solution. And a particular solution, you're going to fill the c in, so you have 3x cubed minus your 2x squared plus 5x plus 10. And once again, this is called the particular solution because it will travel through one point in particular. Now, for number 2, look at that. Oh my goodness. You weren't given a derivative, you were given the second derivative. All right. So you were also told that f at 2 is 8, f prime at 1 is 3, and you are to find f of x. So if you integrate both sides, you get f prime of x equals the integral of 7/3 x to the -3 dx. In which case, I'm going to factor that 7/3 out just to get it out of my way, and just think about x to the -3 dx. Add 1 to your exponent, divide by the new exponent, and we have x to the -2 over -2 plus c. Now, use the information you're given. F prime at 1 equals 3. So it's very important that you understand your notation. F of x is on the left side of all of these equal signs. F prime of x. So f prime of 1 equals, remember this is your x equals 1, and f prime at 1 is equal to 3. So substitute, we're going to have 7 over -6 times 1 to the -2 plus c must be equal to 3. And with that in mind, we know that c equals 3 plus 7 over 6, or 25 over 6. Now, we take our 25 over 6 and rewrite our problem so that we have f prime of x equals your negative 7 over 6 x to the negative 2 plus 25 over 6. But remember, we're not done. I want f of x. Find the antiderivative, and we get f of x equals your negative 7 over 6 times x to the negative 1 divided by negative 1 plus 25 over 6x, and don't forget, plus c. Wait, we have another piece of information that we haven't used. F of 2 is equal to 8. So what does that tell us? F of 2 equals positive 7 over 6 times 1 over 2 plus 25 over 6 times 2 plus c must be equal to 8. So that was given to us. Solve this again for c. We know that c is negative 11 over 12. Not finished though. Remember, you are supposed to say what f of x equals. F of x equals, simplify things a little bit, we're going to get a nice positive 7 over 6 times 1 over x plus 25 over 6x. Replace the c with negative 11 over 12. So these are called initial value problems. You are given your initial values so that you can find your particular solutions and replace those c values. How these become useful is we can use them to solve position, velocity, and acceleration problems. For our third example, we have a ball thrown upward with an initial velocity of 72 feet per second from a height of 100 feet. So there's a lot of information given here. What we're given is that the velocity at time 0, that's what initial velocity means, was equal to 72 feet per second. The initial height, so that's s of 0, is equal to 100 feet. So feet per second and feet. Find your position function given that the height is a function of time. All right, now the thing that you are not told is that the gravitational pull is your acceleration. And gravity is constant. So the acceleration at 0 or any time t when you're playing with feet, negative 32 feet per second squared. So our acceleration at any time t, negative 32 feet, is 32 feet per second squared. All right, now, if we integrate our acceleration, the integral of something measuring feet per second squared gets multiplied by dt, which is seconds, your answer has to be in terms of feet per second, which you know is velocity. So your velocity at any time t is the integral of your acceleration function. And in this problem, that's going to be negative 32 feet per second squared. Unfortunately for us, we know that the velocity at 0 is equal to 72. So v at 0 is 32 times 0 plus some sort of constant must be equal to 72, tells us that our velocity equation, v sub t, is equal to negative 32t plus 72. All right, now we were told to find the position function. We're not there yet. But if I were to integrate velocity with respect to time, that would be the units feet per second multiplied by seconds, and that, of course, leaves us with feet. So position function is equal to the integral of your velocity function with respect to time. We use those units to help figure this out. And when I integrate, we'll get our negative 16t squared plus 72t plus some sort of constant of integration. All right, now given that s at 0 is equal to 100, that tells us the c value will be 100 and leaves us with s of t is your negative 16t squared plus 72t plus 100. All right, now what is the position of the ball when it hits the ground? Now when a ball hits the ground, its position is going to be equal to 0. And the reason I wanted to point that out is that often you're asked, when does the ball hit the ground? So you want to take your s of t, set it equal to 0. In this case, we're going to take our negative 16t squared plus 72t plus 100, set it equal to 0, and solve that equation. You can use a calculator for that, and we come up with 5.613 seconds is the time that we're going to take until we hit the ground. So question D is asking, how can we use the position function to determine the total distance the ball traveled? Now remember, the ball goes up. So for your position function, take a look at your graph. You can find the maximum value of the graph occurs when you have the time 2.25 and the height is 181. So if your initial height was 100 and you go to 181, while traveling upward, the ball went 81 feet. And then to get back down to the ground, it has to go another 181 feet. So in order to use the position function, you can determine the total distance traveled by adding the upward component and the downward component. But you can use your velocity function to determine the total distance traveled as well. So if you were to integrate from 0 to when you hit the ground, so that was your 5.613, the absolute value of your velocity function, that's going to take into account how far up and how far down the ball goes. So your velocity function can be used to find your total distance. This is total distance, not your position. So let's sketch a quick graph of your velocity function. As you'll recall, your velocity function was negative 32t plus 72. So it went up 72 feet and then down 32 and over 1. It hit 0 at 2.25. So you can see that until you get to 5.613. You have positive area because you're heading upward with that ball, and then under the axis you have negative area. So if you were to find the area of each of these triangles and add them together, that would give you your total distance if you treat them both positive. Net position or displacement, you would take your positive and your negative to combine them. So there's a lot going on here. Your total distance versus your net distance. So let's summarize what we've talked about today. Your equation, y equals the integral of f of x, has many solutions. And you can see from this graphic we've drawn that depending on what your c value is, that's going to be the solution you're looking for in particular. C is that constant of integration. And if you can figure out your c value, that tells you your particular solution. Your position function is the integral of velocity. And then you add where you started. Your velocity function is the integral of acceleration. And then you add your initial velocity. Displacement is the shortest distance from your initial point to your final position. That's the integral of velocity. Now, there's a relationship. Acceleration is the derivative of your velocity, but that's the second derivative of your position. We have some more definitions here for you, so you can use this as a handy reference. Average velocity is defined as the displacement divided by time. Speed is the absolute value of your velocity. Acceleration can be defined as the instantaneous rate of change of velocity. Your average rate of change can be the difference of whatever function you're dealing with divided by time. And total distance is the integral from A to B of the absolute value of your velocity. So just a couple of reminders about slope fields. The slope fields work very well with integration. We're going to find a particular solution first, separating our variables. dy equals negative x to the negative 2 dx. Integrate both of our terms. We have y equals negative x to the negative 1 divided by negative 1 plus c. Now we're told that we're going to pass through the point 1, 3. So 3 must be equal to positive 1 plus c, or c equals 2. So the function we're dealing with is y equals 1 over x plus 2. Graphing that function. All right, so now what we know is that we're passing through 1, 3. We're going to follow our slope fields as best we can and make certain that the lines you draw are parallel to the lines within your slope field. And you should have a lovely drawing. Now this problem, I probably shouldn't have touched the number 2 because it looks like I'm approaching 2 but never touching it. For the next example, number 5, you're supposed to draw that slope field through dy dx and then determine your particular solution. I wanted to remind you of how to do these. So when you make your table of values, you're going to pick out your x's in this problem and figure out your dy dx. So if I let x be 0, my dy dx is negative 1. So anytime my x's are 0, I'm going to draw a slope down 1 over 1, down 1 over 1. Now what if I let x be 1? Then my slope seems to be negative 3. Down 1 over 3, way steeper, and these are all parallel, so that's helpful. Next, when I put in negative 1, I'm going to get a slope of 1. So all of my slopes at negative 1 go up 1 over 1. Placing in my next one, negative 2, gives me a slope of 3, which makes this way steeper. And I try to draw them parallel and steep. Okay, now use your separation of variables. dy equals negative 2x minus 1 dx. Integrate both sides. Y equals negative 2x squared over 2 minus x plus c. We know that when x is 0, y is 3. So y equals negative x squared minus x plus 3. And if I try to graph this, I'm going to plot 0, 3, 0, 1, 2, and 3, draw my line in, and then follow what the graph is doing. And hopefully what you recognize is that this is a quadratic equation, and you want to be as careful as you can to make your slope field work. There we go. All right, so let's look at our practice problems for today. So as you'll recall, slope fields are graphical representations of your derivatives, and now you can actually draw your integrals within those slope fields. All right, give this practice set a try, and turn the video off, come back, check 1 or 2 of your answers once you've completed the work. All right, so for question number 6, part A, how high does the rock go? Really want to know, when does v of t equal 0, which happens at 30 over 1.6, and then figure out s of 30 over 1.6. How long was the rock aloft is asking, when does that rock hit the ground, or when does s of t equal 0? At what time was the velocity equal to 16? Okay, take your velocity equation, set it equal to 16. Lastly, what is the speed of the rock? Remember, speed is the absolute value of your velocity. For question number 8, when is the particle at rest? Well, it's at rest when your velocity is equal to 0. When is the particle speeding up or slowing down? Excuse me, is the particle speeding up or slowing down at t equals 1? So figure out v at 1, figure out a at 1. If the signs are the same, your particle is speeding up. If the signs are different, the particle is slowing down. All right, give page 251 a try, and you have a fabulous day.